Welcome to The Deep Dive, the show where we take a monumental stack of complex material, the research, the theory, the equations, and distill it down to the essential, mind-blowing nuggets you need to know.
Today, we aren't just looking at a field of science. We're opening up what is really the foundational text for a huge part of materials engineering.
We're diving into how the very building blocks of modern technology are made.
Exactly. From the sensitive ceramic components in your phone to the pigments and high-end coatings, we're talking about how these things are reliably created.
And we're talking about materials science, specifically this process of using incredibly tiny particles suspended in a gas, an aerosol, to build things.
Right. And when most people hear aerosol, they immediately think of, a spray can or maybe air pollution.
Sure.
But in the world of advanced manufacturing, the aerosol is, well, it's the ultimate manufacturing tool. It's capable of delivering these extremely pure, highly controlled building blocks.
Our source material for this is a landmark text, Aerosol Processing of Materials by Kodas and Michael J. Hampden-Smith. It came out in 1999, but the principles it lays out, they're timeless.
Absolutely. The fundamental physics, the chemistry, the transport mechanisms, this stuff underpins all modern particle synthesis.
So our mission today is pretty straightforward, but it's rigorous. We're going to chart the foundational science of aerosol behavior, and we're going to do it by following the logical progression of the book itself.
We'll start by defining what an aerosol even is in this context. Then we'll get into the really strange size-dependent physics that govern how these tiny particles move.
And then from there, how they grow and collide with each other.
And finally, we'll look at the critical role of the precursor chemistry that makes the whole process work in the first place.
So essentially, we're going to understand the engineering challenge that takes you from, say, a volatile chemical all the way to a perfect nanophase powder.
Or a high-performance thin film. It's a journey from individual molecules through fundamental physical laws and right up into large-scale reactor design.
Okay, let's unpack this, starting with the basics. For our purposes today, what exactly defines aerosol processing?
At its core, aerosol processing is just the synthesis of solid or liquid powders and films using particles suspended in a gas.
Simple enough.
But the first thing you have to grasp is the size scale. It's huge. The particles can range from molecular dimensions, I'm talking a few nanometers, all the way up to roughly 100 micrometers.
100 micrometers. That's still less than the thickness of a human hair, but scientifically, that's an enormous range.
It's a massive range. And that scale difference is, is key to the entire field. We'll see that later when we talk about transport.
Okay, so the book mentions that historically, aerosol science was kind of rooted in the negative.
It was, yeah. Researchers were mostly studying the harmful effects. Things like air pollution, contamination in semiconductor clean rooms, the health hazards of inhaled particles.
And even things like dust explosions.
Exactly. Dust explosions in industrial settings.
Yeah.
So the initial research was all about understanding how to mitigate the danger of aerosols.
So what was the big shift? The aha moment?
The aha moment for modern materials science was when engineers and chemists realized that if they could, control these phenomena instead of just fighting them, they could use them for incredibly beneficial manufacturing.
Right. And what are some of the heavy hitters here, the really sophisticated materials that are made this way? Because this is where the engineering is just incredible.
The list is vast.
Yeah.
I mean, it's critical to modern tech. Take ultrafine titanium dioxide, text TiO2.
The white pigment.
The white pigment, yeah. But it's also crucially used in cosmetics. The nanophase particles go into sunscreens because they absorb UV light really effectively without leaving that, visible white residue.
I use that every summer, and I never once stopped to think that the reason the sunscreen goes on clear is because of this incredibly precise aerosol process.
And that pigment is produced primarily by what's called gas-to-particle conversion.
What else is on that list?
Well, you find aerosol routes used to create thin films for flat panel displays, high-performance windows. Think about high-purity optical fibers. They need this extreme level of structural uniformity.
And you can only get that with this kind of controlled deposition?
Exactly, from the gas phase. Another huge application is multi-layer ceramic capacitors, or MLCCs. These tiny components need highly controlled submicron ceramic powders like barium titanate with perfect stoichiometry to work inside an integrated circuit.
The source even mentions high-temperature superconductors, materials like YbCO. That's a notoriously difficult class of material to synthesize.
It is. And it speaks volumes about the control offered by aerosol methods, that these complex multi-element ceramics can be made reliably using particles carried by a gas.
So that material complexity really gets to the core engineering challenge, which is managing all the physicochemical phenomena.
Right. And if you look at the diagrams in the book, you see immediately why this is so complex. Aerosol methods are not a sequence of steps. They're more like a dance of simultaneous physical and chemical processes.
A dance where if one partner speeds up or slows down, the whole thing just fails.
Precisely. You're talking about gas phase reactions, the chemistry happening in the gas, running alongside single particle processes like surface reactions or evaporation.
And then you have to factor in how the particles interact with each other.
Yes, the multi-particle phenomena, collision, coalescence, and agglomeration. These processes determine the final structure of the powder you harvest.
So if they collide but don't fuse, you get what? A clump?
You get weak, hard-to-break-up aggregates. If they collide and do fuse or coalesce, they change size dramatically, and you lose that desired nanophase structure. It's a fine line.
So if I'm designing a reactor, I have to model fluid flow, heat transfer, chemical reaction kinetics, and particle collision dynamics, all at the same time. That sounds like a simulation nightmare.
It's a phenomenal modeling challenge. You also have to manage gas phase nucleation, the birth rate of new particles, and chemical vapor deposition, or CVD, where material deposits as a thin film.
And I'm sure things can go wrong.
Oh, absolutely. You have to worry about sintering, which is the fusion of particles, and even re-entrainment, where material that is already deposited on the reactor wall gets swept back into the gas flow and acts as a contaminant. You have to keep all these dials stable simultaneously.
Let's look at the different production strategies the book details. It seems like they fall into a couple of major categories.
Broadly, yes. The first is gas-to-particle conversion. This is where your precursors are introduced as a vapor, and then they chemically or physically convert directly into solid particles.
So the particles are born right there in the gas.
Exactly. The key here is that it always requires extremely high supersaturation to drive the nucleation and growth of that new phase.
And what are some examples of that?
High-temperature routes like combustion synthesis, flame pyrolysis, or even highly localized methods like laser ablation, which can produce these really exquisite materials like rhodium nanopowders.
Okay, so that's starting from a gas. What's the second strategy?
The second is the intraparticle reaction route. This process starts not with a gas, but with a liquid droplet, and the reaction happens inside that droplet or the solid particle that forms from it.
The classic example being spray pyrolysis.
The classic example is spray pyrolysis. You atomize a solution with your precursor into fine droplets. Those droplets are then dried, and the precursor either reacts or decomposes within the confines of that solid particle.
That sounds like a crucial distinction. In gas-to-particle, the reaction environment defines the particle. In interparticle, the original droplet size basically sets the final particle size.
You've nailed the distinction. And of course, there are also hybrid processes that combine the two. Things like aerosol-assisted CVD, where you might use a liquid aerosol to deliver a precursor, but then rely on gas phase reactions to form the film.
So understanding why an engineer would go through all this complexity brings us to the advantages and disadvantages. What are the major selling points for using aerosol routes?
For making powders, the benefits are huge. They allow for exceptionally high purity, which is critical for electronics. You can get very controlled particle size distribution, or PSD, and specific morphology.
So you can choose if you want nanophase materials or single crystal structures.
Or specific shapes, yes. The process is also often continuous, energy efficient, and crucially, dry.
That dry processing benefit seems enormous. It avoids all the time and contamination you'd get from removing solvents, washing, and all the purification steps you see in traditional wet chemistry.
Exactly right. And for films, the advantages are also clear. High deposition rates, a generally simpler process configuration compared to, say, vacuum CVD, and the ability to use low volatility precursors that might be too heavy or complex to vaporize in a traditional setup.
But nothing is perfect. What are the engineering headaches?
The biggest headaches are usually control-related. It can be really difficult to control the precise stoichiometry.
Meaning ensuring the ratio of elements in the final product is exactly right.
Yes, especially for multi-component systems like superconductors. Another big one is that hard agglomerates are frequently formed. These are particles that have sintered together and are extremely difficult to break up, which reduces the quality of the final powder.
And despite aiming for high purity, you can still get contamination.
You can. If you use liquid routes like spray pyrolysis, you might have residual solvents left over. In any route, you risk contamination from residual particles or from the reactor walls themselves. It means reactor design is always this delicate balance of flow rate, temperature, and residence time.
This brings us right to the physics of scale. We're talking about particles from nanometers to micrometers. The laws of physics that govern their movement can't possibly be the same across that range, can they?
They absolutely are not. And this is where we step away from fluid dynamics as we, understand it in our macroscopic world and enter the strange realm of the Knudsen number.
Okay, before we get to the Knudsen number, we need to understand the mean free path.
Right. The mean free path, lambda, is simply the average distance a single gas molecule travels before it smacks into another gas molecule. In air, at standard conditions, this value is tiny, about 0.067 micrometers or 67 nanometers. That's our fundamental ruler.
67 nanometers. Okay, so how do we use that ruler to categorize our particles?
We use the Knudsen number, or no dollars. This is a dimensionless ratio. It's the gas mean free path, lambda, divided by the particle's diameter, dp/L. And this ratio tells you everything about how the particle will behave.
So if the particle is huge compared to the distance gas molecules travel, the Knudsen number is very small. Let's say it's much, much less than 1.
That puts you in the continuum regime. The particle is so large, say 10 or 20 micrometers, that it basically sees the gas as a continuous fluid like a boat in water. Its movement is governed by familiar fluid dynamics, and you can predict drag using classic equations like Stokes' law.
But when the Knudsen number is very large, when the particle is actually smaller than the distance the gas molecules travel between collisions, you're in a completely different world.
You are. Not much greater than 1 defines the free molecule regime. This is where nanoparticles live, usually anything much smaller than about 0.1 micrometers. In this world, the particle's movement isn't determined by smooth fluid flow.
It's just getting bombarded by individual molecules.
Exactly. Random, discrete collisions, molecular bombardment. The drag equations change completely. They depend on momentum transfer, not viscosity. This distinction is the bedrock of aerosol physics. If you model a 50 nanometer particle using continuum dynamics, your results will be completely wrong.
That just highlights the incredible precision needed to even start modeling the system. Next, the source talks about mass and particle concentration. Why is concentration so critical?
Particle concentration, the number of particles per cubic centimeter, is the direct driver of collision frequency. And collision frequency dictates growth via coagulation.
So high concentration means particles collide quickly and grow fast.
Right. The challenge for the materials scientist is balancing the need for high concentration to get good production throughput against the desire to minimize collisions to keep the particles small.
Can you give us a sense of the scale here? What are the extremes?
Think about this. An industrial facility making TiO or carbon black might operate at concentrations as high as 177 sus particles per cubic centimeter.
Okay.
Now, contrast that with a semiconductor fabrication clean room. They have to maintain a concentration of less than 1 particle per cubic centimeter to avoid catastrophic defects on their chips.
That's 7 orders of magnitude difference, all depending on whether your goal is mass production or absolute total contamination avoidance.
It really brings home how tightly controlled these environments are. And that leads to the next major characteristic, the particle size distribution, or PSD. Materials processing is useless if the particle size is uncontrolled, because size dictates properties.
Everything from catalytic activity to optical clarity.
Everything. So we need a way to mathematically describe this distribution.
And that's usually the log normal distribution.
Often, yes. It's defined by 2 values.
Yeah.
The geometric mean diameter, which tells you the average size, and the geometric standard deviation, sigma, which tells you how spread out the sizes are.
And the source gives us a specific dividing line based on that standard deviation, right?
It does. A value of sigmag 1,555 is often taken as the dividing line. If your value is close to 1, say 1.1 or 1.2, your aerosol is considered monodispersed.
That's the holy grail, right? All the particles are nearly same size.
It's the goal for many applications. If sigmag is much greater than 1.5, it's polydisperse. You have a very wide spread of sizes. And in those cases, you have to be very careful because different ways of calculating the average diameter can give you wildly different numbers.
So achieving a sigma close to 1 is a sign of exceptional process control. Now, what if the particle isn't a neat little sphere? That brings us to morphology.
Right, because most real-world particles aren't perfect spheres. They can be rods, cubes, fibers, or most commonly, complex agglomerates and aggregates.
What's the difference?
Agglomerates are composed of smaller primary particles held together. If they're just stuck together by weak van der Waals forces, they're soft and can be broken up. If they've started to sinter or fuse at the neck, they're hard and become permanent structures.
And there's a really sophisticated way to describe the geometry of these tangled messes. The fractal dimension, dollars.
It's a fascinating concept. The fractal dimension quantifies the irregularity and the openness of these aggregates. A perfect solid sphere has a fractal dimension of 3.
It fills space completely.
Right. But these open, branched, chain-like aggregates that form in high-concentration processes, they typically have a d-dollars between 1 and 2. The number tells you how much empty space is contained within the aggregate structure.
Why does that matter for the final product?
An aggregate with a low DLO4, say 1.5, is much more porous and open than one with a d-doll closer to 3. This dramatically impacts everything. How it deposits, how much surface area it has for catalysis, how it reacts. If you're using this aerosol to make a filter, the fractal dimension is everything.
Okay, next up is chemical composition and phase composition. If I'm making a multi-component material like that TXB-TO3 ceramic or a superconductor, I need every single particle to have the exact same ratio of elements.
And achieving that uniformity is notoriously difficult. Differences in the volatility of your precursors or varying transport rates can lead to what's called inhomogeneity.
So one part of the particle could be different from another part?
Exactly. For example, one element might condense or react faster than another. You end up with a particle where the surface is rich in component A and the core is rich in component B. That kind of variation destroys the material properties you're targeting.
And the final piece of the particle's identity is its internal arrangement, or its crystallinity.
The structural state, whether it's amorphous and disordered or crystalline and ordered, profoundly dictates the final properties.
So electronic, optical, magnetic properties.
All of it.
All of it. The book uses the excellent example of barium titanate TXB-83. To work as a capacitor or a sensor, it has to be in a specific crystalline phase, the tetragonal phase. If your processing temperature or residence time is too short, you end up with an amorphous powder or the wrong crystal structure, and the material just fails.
So process control here means getting the size, the composition, and the exact atomic arrangement right.
It's all three. So we've established the identity of the particle. Now we have to understand how it moves. This is transport, and it dictates the entire outcome, right? Does the particle stay suspended to be collected as a powder, or does it deposit precisely where we want it to form a film?
Transport phenomena are the whole game. They're governed by fluid flow, temperature gradients, gravity, and electric fields. And these are the forces that let engineers direct particles to form high-purity optical fibers or create a homogeneous film using aerosol-assisted CVD.
Let's start with the movement mechanism that's most common in the submicron world, diffusion.
Diffusion, or Brownian motion, is that fundamental random movement caused by the ceaseless, uneven bombardment by gas molecules. Because the particle is small, its motion is just dominated by these random collisions. Diffusion is the key mechanism for particles typically below 0.1 micrometers.
And the crucial engineering consequence of diffusion is something called wall losses.
Exactly. Diffusion is the main reason small particles randomly wander off and stick to the cooler reactor walls, especially in smooth laminar flow systems. This directly reduces the yield of your collected powder.
So the smaller the particle, the harder it is to control its trajectory against this random walk.
Absolutely. So an engineer has to design the reactor length and flow rate to minimize the time the particles spend near the walls if they want to maximize their yield.
Okay, so that's random motion. What about the intentional forces from external fields? Let's start with one that seems obvious: sedimentation in a gravitational field.
Our intuition tells us things fall, but the source makes it clear. Gravity is often a negligible force in aerosol processing.
Why is that?
For these tiny particles in a gas, the drag force from the surrounding gas molecules is just huge relative to the tiny gravitational force. The book gives a powerful example. A 1 micrometer TEX TiO22 particle settles at only 3 tollers 7 centimeters times 10 3 centimeters per second.
Wait, that's 37 micrometers per second. That means it takes over 45 minutes for that particle to settle just 10 centimeters.
It's practically floating. Sedimentation really only becomes a dominant force if you have very large, very dense particles, or if your reactor has extremely long residence times. In most high-throughput processes, gravity is just irrelevant compared to the speed of the gas flow.
So if gravity is too weak, a much more effective force is the electric field, using electrophoresis.
Electric fields are incredibly useful. The mechanism relies on the particle acquiring a charge, either through friction or collision with ions. Once it's charged, you can use an electric field to pull it toward an electrode.
This is the principle behind electrostatic precipitators, right? For cleaning smokestacks.
It is, but it's also used directly in high-precision deposition. What's fascinating is the sheer power of it. The electrophoretic deposition velocity often dominates all other transport mechanisms for particles up to a micron in diameter. It allows for extremely high efficiency collection.
So if you want a uniform film or a high collection yield and you can charge your aerosol, an electric field is the way to go.
It's often the solution, yes. It's the basis for collection in a lot of advanced spray pyrolysis systems.
But there's a force that is arguably the most common and often the most problematic in industrial reactors, and that's the one generated by temperature differences, thermophoresis.
Thermophoresis is the movement of particles caused by a thermal gradient. Simply put, particles move from hot surfaces toward cold surfaces.
How does that work?
It's because the gas molecules on the hot side are moving faster, so they strike the particle with more momentum than the gas molecules on the cold side. The net result is a force pushing the particle away from the heat.
So if I have a high temperature reactor where I'm making my powder and the walls of the reactor are cooled,
Thermophoresis drives every particle toward those cooler walls. This is why the source calls it the single most common loss mechanism in industrial reactors. You lose valuable product to the walls simply because of that unavoidable temperature difference.
but you mentioned engineers can turn this bug into a feature. How do they exploit it?
They use it for high-purity synthesis and separation. In the commercial production of textile-to-wood pigment, or in making optical fibers, the reactor is designed to intentionally create a thermal gradient that drives the particles out of the bulk gas flow and onto a cool target.
So you use the force to cleanly separate the valuable product from the gas stream.
Exactly. You get a very clean, high-yield deposition. It's a classic case of taking a fundamental physical nuisance and weaponizing it for manufacturing.
So the opposite of diffusion is impaction. What's that about?
Impaction is all about inertia. This is for larger, denser particles moving at high velocities. Because of their mass, they resist changes in their direction when the gas streamlines curve, say, around a baffle.
Their momentum carries them straight ahead.
Their momentum carries them across the streamlines, causing them to impact the surface. So small particles follow the gas streamlines and diffuse randomly, while large, fast particles ignore the streamlines and hit the target because of their inertia.
And all these mechanisms, diffusion, thermophoresis, impaction, they all determine the final structure of the deposit.
Yes, the porosity, the density, the smoothness of the final film, or powder, it's all a direct consequence of the dominant transport mechanism. Understanding that regime is essential before you even start thinking about the chemistry.
Okay, as we move deeper into the particle's microscopic life, we get to the dynamic trio that determines its final size: condensation, evaporation, and nucleation. I want to jump into a concept that is really counterintuitive: the relationship between size and stability, known as the Kelvin effect.
This is a huge one. It governs particle growth in the free molecule regime. Growth happens when vapor molecules attach to the particle surface, and the rate is driven by the degree of supersaturation, how much extra material is in the gas phase compared to what the particle's local environment can support.
And the Kelvin effect is what messes with that equilibrium.
It does. The Kelvin effect states that the vapor pressure over a curved surface, like the surface of a tiny particle, is higher than the vapor pressure over a flat surface of the same material.
Okay, and the implication there is profound. Because small particles have this artificially high local vapor pressure, they need a much, much higher degree of supersaturation in the surrounding gas just to survive.
Precisely. Just to maintain their current size, let alone grow. If the supersaturation is only moderate, the smallest particles will immediately start to evaporate or sublime, giving their mass back to the gas phase.
It's like the constant threat of extinction for the smallest building blocks.
It is. The Kelvin effect establishes a critical particle size. Below that size, which might be around 1 nanometer for something like TeX-Ti2, the particle simply isn't stable and can't survive. It's forced to evaporate.
Wow. Okay, so we see the reverse of that in droplet evaporation, which is central to liquid-based routes like spray pyrolysis.
Right. In spray pyrolysis, you start with a liquid droplet, and you need that solvent to evaporate really fast so the precursor can form a solid particle before it starts to decompose or react.
And the timescale here is incredibly short.
It has to be. Small droplets, say 0.1 micrometers in diameter, have evaporation lifetimes measured in seconds or even milliseconds. The engineering constraint is this: the evaporation time has to be shorter than the residence time in the reactor before the chemistry kicks in. If it's too slow, you deposit wet, sticky material, which just ruins everything.
Beyond phase changes, particle size also changes through surface chemical reactions. When precursors react and deposit material onto an existing particle, how does an engineer control that rate?
They have to identify the rate-limiting step. There are two main possibilities, and each has a different relationship with the particle size.
Let's start with the first one, where physical transport is the bottleneck.
That's the gas phase transport limitation. In this case, the chemical reaction on the surface is very fast, but the reactants diffuse slowly through the gas to get to the particle. Because the diffusion is related to the particle diameter, dp/tor, the growth rate is proportional to dpo.
And the second possibility is when the chemistry itself is the slow part.
That's the surface reaction limitation. Here, reactants arrive at the surface quickly, but the reaction itself is slow. Since the reaction happens over the whole surface, the growth rate is proportional to the particle's surface area, which is proportional to dp/2.
So if I'm in the transport-limited regime, the rate is proportional to dp2. Larger particles grow a bit faster, but in the surface reaction-limited regime, the rate is proportional to dp22. Larger particles grow quadratically faster. That's a massive difference.
It's the key to control. If you want to maintain a monodisperse aerosol, you often want to avoid that dp/2 dependence because it causes the larger particles to just gobble up all the available material, which widens your size spread.
And finally, we have to talk about the very beginning of the process, nucleation, the birth of a particle.
Nucleation is the formation of new, stable clusters, a new phase from a supersaturated vapor. It is the defining moment that determines the total number of particles you'll have in your system.
And there are two main types, right?
Yes. Homogeneous nucleation is self-nucleation. Think of water droplets forming in clean, supersaturated air. Heterogeneous nucleation involves foreign species dust, ions, the reactor walls, acting as preferred sites for condensation.
And in manufacturing, heterogeneous is much more common.
Far more common, because the presence of surfaces and impurities drastically lowers the energy barrier needed to form a cluster. It's just easier for a molecule to stick to something that's already there.
Now, let's bring in classical nucleation theory, or CNT. What does it tell us about controlling particle birth?
CNT gives us a terrifying insight. The nucleation rate, J, which is the number of new particles formed per second, is exponentially dependent on the saturation ratio, S.
Exponentially. That means process control has to be razor sharp.
Absolutely. A tiny fluctuation in temperature or pressure, which causes the tiny change in S, can trigger a massive burst of new particles. You can go from forming 10 particles per second to 10 billion per second almost instantly.
Which leads to an uncontrolled polydisperse aerosol.
Exactly. While CNT is complex and not always quantitatively perfect, it's a powerful reminder of just how extremely sensitive particle birth is to your process conditions.
Okay, so we've covered how an individual particle is born, lives, and moves. Chapter 5 tackles what happens when they all get together. Coagulation, particle collision.
And this is the single most dominant factor affecting the final particle size in high-concentration systems. Coagulation is the primary way particle size increases in almost every industrial aerosol process.
It's crucial for things like carbon black, fumed silica, and TiO2.
Absolutely. And we should start with the most fundamental driver, Brownian coagulation. This is just the random thermal motion of gas molecules causing the particles to randomly walk around and bump into each other.
And at industrial concentrations, the collision frequency is astronomical.
It is. To quantify this, the source introduces the coagulation time. That's the time required for the total particle concentration to drop by half because of collisions.
And this timescale is where the practical engineering challenge becomes terrifyingly clear.
It does. Consider 0.1 micrometer particles at a pretty typical industrial concentration of 10 particles per cubic centimeter. The coagulation time is measured in milliseconds.
Milliseconds. So if I design a reactor where the aerosol spends 100 milliseconds in that high concentration zone, the particle concentration will have been cut in half multiple times over, and the particle size will have ballooned.
That is the ultimate constraint on reactor design for making nanophase materials. If you want small, monodisperse particles, the residence time in that hot, concentrated zone has to be shorter than the millisecond timescale for collision. You have to get the product out of there, either by rapid cooling or high-speed flow before coagulation ruins it.
Beyond random motion, collisions can be driven by the bulk gas flow itself. That's shear-induced and turbulent coagulation.
These become important in large-scale industrial flows with high Reynolds numbers, so high velocity and chaotic mixing. Shear-induced coagulation happens because of velocity gradients. Turbulent coagulation is driven by the swirling, chaotic eddies in the fluid.
And these bulk flow mechanisms mostly affect the larger particles.
Correct. The Brownian mechanism fades as particles get bigger, and these inertial and fluid dynamic forces take over.
Okay, here is arguably the most mathematically elegant concept in the whole process, the idea of self-preserving size distributions, or SPSDs. This suggests that despite all this chaos, there's an underlying order.
This is the moment where chaos finds a fixed point. It's beautiful. Despite the constant collision and coalescence and the continuous growth of the average particle size, the particle size distribution naturally trends toward a stable, characteristic shape, the SPSD.
So even if the average size is growing from 50 nanometers to 100 nanometers, the relative spread of the distribution stays the same over long timescales?
Exactly. The practical relevance for an engineer is huge. It means they don't have to constantly fight to maintain the shape of the distribution. Once the system reaches SPSD, they only need to control the scale, which simplifies modeling and predicting the output quality.
And the source connects the mathematical shape of that SPSD directly back to the physical structure of the particle itself.
Right. It does. The specific shape of the SPSD depends on the fractal dimension, d-Ehlers, of the agglomerates being formed. The distribution for compact spherical particles is narrower than the distribution for open, fluffy, chain-like aggregates. It's a remarkably complete piece of theory.
That brings us to the final fate of colliding particles. They don't just stick, they fuse. That's coalescence, or sintering.
Coalescence is the process where colliding particles fuse together into a single, less porous and often spherical particle. It's driven by the reduction of surface energy and is typically activated by high-temperature thermal sintering.
And like coagulation, the timescale for this is incredibly sensitive.
It's exponentially dependent on temperature. The higher the temperature, the faster the sintering. The book gives a great example. Sintering 10 nanometer text TiO2 particles takes about 1,000 seconds, around 16 minutes at 800 Kelvin. If you raise that temperature by a few hundred degrees, that time might collapse to seconds.
This reveals the razor's edge an engineer has to walk. You need high temperatures to drive the chemical reaction, but if the temperature or the residence time is too high, the particles fully sinter and you lose the desirable nanophase characteristics.
You are constantly managing the race between reaction time, collision time, and sintering time. You have to design the reactor to do the chemistry, then rapidly quench the process to prevent unwanted coagulation and oversintering.
We jump now to the fundamental chemical choices that underpin this whole physical process. The physics of transport and collision are totally dependent on the chemical reagents we pick.
Chemistry is the absolute linchpin. It dictates everything. Composition, purity, stoichiometry, and ultimately the final particle size and structure.
And the first, most critical decision is the selection of chemical reagents as precursors. The source identifies 3 key properties that have to be balanced: solubility, volatility, and reactivity.
Starting with solubility. This is the gateway property for liquid phase routes, like spray pyrolysis. The precursor has to dissolve in the solvent to form a stable solution. If it doesn't, it might precipitate out and clog the system before you even start.
Next is volatility, which is essential for gas phase routes like CVD.
Volatility is the ability of the precursor to turn into a gas. It depends exponentially on temperature. If your precursor isn't volatile enough, you simply can't get it into the reactor in the vapor phase, which is a requirement for homogeneous nucleation and high-purity CVD.
You often have to heat the precursor tanks themselves just to get enough vapor pressure.
All the time. And the third property, reactivity, dictates the success of the whole thing.
How so?
Reactivity determines the rate and, critically, the pathway of the reaction, including any byproducts. You need to know that whole pathway to control purity. If the reaction produces undesirable byproducts, say carbon residue from an organic precursor, that contaminates your final material. You need a precursor that reacts cleanly and predictably.
Let's dive into the common types of thermally induced reactions, starting with inorganic compounds.
A classic example is the decomposition of metal nitrates. They're widely used because they generally decompose pretty cleanly to the metal oxide you want, releasing harmless gases like textose 10-2.
But the decomposition temperatures are all over the place.
Wildly different. Aluminum nitrate decomposes around 150 Celsius, while strontium nitrate needs 550 Celsius. That huge range means the reactor geometry and heating profile has to be custom designed for every material. You can't just swap them out.
What else?
We also see metal carbonates, especially in spray pyrolysis,
Mm-hmm.
and metal halides like Te4,4, which are extremely volatile and are the foundational precursors for high-purity materials like optical fibers and TeTO2 pigments.
Now, what about metal organic compounds? These often solve the volatility problem, but they introduce the risk of carbon contamination, don't they?
That's the core trade-off. Metal carboxylates are used, for example. But the stars of volatility are often the metal beta-dictinates. They're highly volatile, which makes them ideal for CVD.
But you have to be really careful to get rid of all that carbon.
You have to use extreme thermal conditions to ensure all the carbon ligands are completely combusted. Otherwise, you get undesirable carbon residue in your final ceramic material, and if properties are ruined.
Finally, let's look at the highest energy routes, plasma-induced reactions. This involves temperatures that are just hard to comprehend.
Plasmas offer these extreme, non-equilibrium conditions. You have thermal plasmas, which are characterized by incredibly high temperatures, from 1,000 degrees Celsius up to 40,000 degrees Celsius.
40,000 degrees, and the residence times are equally extreme.
Down to 10 to 5 seconds, microseconds. This high energy is perfect for making materials with very high melting points, like specialized ceramics, where a traditional furnace just can't get hot enough.
And what about the alternative, the gentler plasma route?
Those are glow discharges, or low-temperature plasmas. They operate at much lower bulk temperatures, but still have high electron temperatures. They're primarily used for depositing thin films onto temperature-sensitive substrates.
So the reactions are driven by highly reactive radicals and ions created by electron impact, not by the bulk heat.
Exactly. It allows you to do complex chemistry without incinerating the substrate you're trying to deposit onto. It's essential for modern microelectronics manufacturing.
It's just so clear that the choice of physical process limits your chemical option, and your chemical choice dictates the thermal conditions, which then determine the transport phenomena you have to manage. It is a stunningly interconnected system.
It's the ultimate feedback loop, and mastering it requires expertise in fluid dynamics, thermodynamics, particle physics, and chemical kinetics, all at the same time.
This deep dive has taken us on a journey from the initial selection of a volatile chemical all the way to the final highly precise crystalline structure of a finished powder or film.
We've really identified the fundamental race that's inherent in aerosol synthesis. You're balancing the reaction time needed for chemistry against the transport time for deposition and the collision time that dictates unwanted growth.
The ability to stabilize a particle against the Kelvin effect, or to exploit thermophoresis for high purity collection, that's what separates a successful manufacturing process from just a pile of contaminated dust.
You now have a comprehensive framework for understanding how these incredibly complex materials, the foundational components of all our advanced technology, are actually engineered.
And we'll leave you with this final provocative thought, building on that mathematical elegance we found in the realm of particle collision. We learned that coagulation, which seems like a totally random, chaotic process, naturally leads high-concentration aerosol systems toward a self-preserving size distribution, a fixed, stable distribution shape, even as the particles themselves are constantly growing.
So if even the violent, high-energy interaction of billions of particles finds this inherent structural equilibrium, consider this.
How might this principle apply to other seemingly chaotic emergent systems? What natural or man-made phenomena like the distribution of wealth or the growth pattern of urban centers might possess their own fundamental self-preserving size or organizational distribution?
And what are the hidden energetic costs when we try to engineer or force that distribution to fundamentally change?
Until next time, keep digging deeper.